Alright, so let's continue our investigation into the origin of the elements. Part 2 has us focusing on processes occurring in the center of stars. So first we'll start with the life cycle of stars, how they start, how they end, then talk about where elements are made within the stars. Lastly, we'll invoke E equals mc squared to try to explain what keeps stars alive for billions of years. So based on the last video, we could account for the formation of hydrogen and helium in the Big Bang. We have all these artificial elements that are only made in labs, but we're still missing the origin story for most of the rest of the periodic table. And just some context here, we ended the last video with the lights going out, essentially, the end of the plasma phase of the universe and the start of these so-called dark ages. Now, there's all this matter that is in the gas phase, essentially, throughout the universe, and gravity starts to act on it and starts to pool that matter together and collect it into sort of swirling balls of gas. Things probably looked a little bit like this. This is an image of a protostar from the Hubble telescope. You can see the gas is sort of collecting here together, and in the center here there's a little bit of light going on here. So what's happening here is that there's enough mass collected here that the pressures inside the center of this protostar are hot enough that we can convert back from a gas phase into a plasma. And as this process keeps going, as this protostar keeps gathering mass from its surroundings, new chemical reactions can be unlocked, essentially. And eventually, a star is born. So this is our sun, sort of looked up close. You can see it's sort of this glowing yellow ball of hydrogen and helium plasma, essentially. So our sun is what's called a main sequence star. It's the most common version of star out in the universe. It forms from a ball of gas called a nebula. Then it turns into this main sequence star once fusion starts happening inside. We'll look at what that fusion reaction actually looks like. Eventually, our sun, like many other stars, will turn into a red giant, and this is sort of the beginning of the end. This is a signal that it's sort of running out of fuel or running out of the ability to keep producing helium from hydrogen, which is its main energy source. This will end up in this kind of decaying planetary nebula, and eventually we'll have this small white dwarf star left behind. Now there's another track for really high mass stars that's quite different, and we'll get to this in the end and also in the next video. These are things that are maybe 25 to 50 times bigger than our sun, so they burn really hot because the pressure inside their center is a lot hotter than our sun. They form these really interesting red supergiants, and then they eventually blow up. And once they blow up in the supernovas, they can form black holes, or they can form these tiny, really dense neutron stars. Okay, so before we get into how a sun actually works, or how a star actually works, I just wanted to do a reminder of the two types of beta decay that we covered in earlier videos. So there's a sort of standard beta minus decay reaction that we talked about with tritium and helium-3. So that's when a neutron turns into a proton and an electron. So that's sort of what turns tritium, which has 2 extra neutrons, into helium-3, which has 2 protons, 1 neutron. There's also this other version called beta positive decay, and that's essentially when a proton converts into a neutron and ejects this little bit of antimatter called a positron. Now, antimatter is a bit complicated, and we don't really need to know the details here. But essentially, what a positron is it's an anti-electron. And when an anti-electron and an electron encounter each other, there's this process called annihilation. Basically, both are sort of destroyed entirely and just converted entirely into energy. So, in beta positive decay, proton turns into a neutron, and then an electron is removed. So we can sort of sum up this process here as a proton and an electron combined to form a neutron, which is the reverse of beta minus decay. Okay, so we'll see why we need to know this right now. So in the center of our sun and in the center of a lot of other stars, the pressures and temperatures are so great that these molecules are flying around. There's a lot of energy, and some of these fusion reactions that were happening at the start of the Big Bang can happen again. So unlike the Big Bang, though, is that there's not a lot of free neutrons around. Right? Neutrons have a half-life of around 10 minutes, and so after the first hour or so of the creation of the universe, there's not a lot of neutrons hanging around. It's just protons here. So fortunately, when 2 protons fuse together, even though there's a lot of positive charge repelling each other, this beta positive decay can kick in. So here you have two protons forming together to form this weird isotope of helium, but then you have this beta positive decay, so you have deuterium formed. And then you have the electron that's ejected, the positron that's ejected, annihilate an electron that's somewhere in the center of the star. So after this process, there's lots more protons flying around that fuse with deuterium to form helium-3. And then once you have enough helium-3 built up, you can essentially have one helium-3 collide with another helium-3, and then that can form helium-4 by bumping off two of these protons. So this is very similar to the one-by-one synthesis that we saw at the Big Bang. Here we're just starting with two protons, and we're ending up again with helium. And this is really how a star has enough energy to counteract gravity. So we can look at this by looking at the balance of mass in this kind of reaction. So we have 4 hydrogens turning into 1 helium, essentially. And if we measure out the mass of the hydrogen that we're starting with the mass of an individual hydrogen atom, it's 1.0078 atomic mass units. So if we multiply this by 4, we should expect that the helium should weigh 4.03 atomic mass units. But in actuality, helium-4 nucleus weighs 4.0026. So I know this is a lot of decimal places here, but we're missing this fraction, 0.03 atomic mass units, which is 0.7% of the starting mass. So basically, helium-4 weighs less than 4 hydrogens, and so we've lost some mass here. And that's where E equals mc squared comes into play. So E equals mc squared, energy equals mass times the square of the speed of light. This is basically a formulation for how much energy is stored within actual mass and matter. And when we're accounting for this sort of missing mass here, what's happened is that's been converted into energy. Essentially, the sun has become a little bit lighter and it's produced a lot of energy through this equation here. And this is really key because this is the only choice that the star has to counteract gravity. There's a lot of mass inside the star, and gravity is going to be pushing it closer and closer in together. But basically what happens is the energy released through hydrogen fusion to helium creates enough energy and enough temperature inside the star that the molecules inside the star can start pushing out against gravity. And so then you have a stable star that's formed. Now we can compare the ways that stars can do this. We talked about fusion of hydrogen into helium. That's going to be actually the most effective way to push out gravity. So here's a plot showing this. On the y-axis is basically the energy released by fusion reactions, and on the x-axis is just the mass of individual nuclei. So if we start here from hydrogen, H1, like our sun does, we can form helium here and we can release a lot of energy here. We're covering almost the entire length of the y-axis just for this first step that we've already covered. But then, once we have enough helium, we can think about what kind of reactions can happen next. But unfortunately, you'll see that this helium is a local high, and there's a big dip when you go down to lithium 6 and 7. And actually, this is the same problem that we saw in the Big Bang, where there's no isotopes at mass 5 that are stable for a nanosecond or so. So this kind of slows things down a lot for most smaller stars. They can't really overcome this valley here, and they get stuck just with a lot of helium in their center and are unable to do anything else. So eventually, that helium fills up the core, and then there's no more fusion that's possible because the hydrogen is pushed out to the edges of the star that aren't as hot, and that's when the star starts to die. However, for the much bigger stars, for these main sequence giant stars, these red supergiants, they can get over this hill. And so essentially what starts to happen is that 2 helium atoms fuse together to form this 8 beryllium nucleus. Now this in itself, this first step, it doesn't actually generate any energy. There's basically the same amount of energy in helium as there is in a beryllium nucleus, so this actually isn't going to be effective at pushing out gravity. But the next step, this addition of another helium to form a carbon-12 nucleus, this puts things back into the black. The cells can generate more energy, or not the cells, sorry. The star can release more energy to push out against gravity by turning helium into carbon. And now we're on this new sort of mode of nucleosynthesis, where we're adding mass units 4 at a time. So the next thing that can happen is this carbon-12 can react with another helium and form 16 oxygen. And this is significant now because if you're keeping score, the goal here is to basically explain some patterns about the ocean at large. And in order to have the ocean, we need to have water, which is H2O. Now we can account for where oxygen is made and where hydrogen has been made. So in these supergiant stars, the process keeps going. So if you were to look down the center of these supergiant stars, you'll see at first there's a core of helium, right? This is the helium that's made from the standard conversion of hydrogen into helium, and this collects in the center because the helium is more dense than hydrogen, so it accumulates in the center of the star. If the star is big enough, there's this additional fusion reaction that's possible that we talked about on the last slide, and this can convert, this produces carbon and it produces oxygen. And if the star is big enough, then the conditions are right for carbon and oxygen to fuse together with some helium to keep forming more and more elements. And so eventually what you'll see is this almost Russian doll where you have cores of different elements. You might have neon, mass 20, magnesium, mass 24, silicon, mass 28, sulfur, mass 32, argon 36, calcium 40. You can see these are all going up by increments of 4, and they're reflecting this sort of helium addition process that's been unlocked. So this process can keep going, right? You can see that we're increasing here. Carbon 12 is above helium 4. Oxygen is above carbon. We can keep getting a little bit of energy out up until we get to iron 56 here. That's the peak of this process. That's the peak of basically energy released by nuclear fusion. And then we flatline for a bit, and then things go down. So once a star has a core full of iron 56, it can't generate any more energy from this. And this is triggers an important event in the lifespan of these large stars, these supernovas, which we'll talk about in the next video. But just to keep track of where we are at this point, we've been able to explain a lot of the light elements. These are formed in to small degrees in most stars, but to a large degree in these very massive large stars that have really dense cores that are really high temperature, and where the even heavier molecules like helium or carbon or oxygen are flying around enough so that they can collide and participate in these fusion reactions. And that explains the formation of elements all the way up to iron here. So we're making some progress, and we'll see how this ends in the next video. So just as a reminder about what to focus on as you're reviewing this content, first we've outlined the life cycle of stars that are both sort of a typical mass range like our sun, but also very the much bigger stars that form these red supergiants. We've described the processes that make different elements, especially carbon, oxygen, and even heavier elements in the center of stars. And we've linked this mass deficit, right? This decrease in mass from hydrogen to helium, that goes all the way up to iron. And that generates energy that keeps the stars alive. It pushes out against the force of gravity that would try to crush the stars.